Hello, everyone, and welcome. Hi, everyone, and welcome to tonight's Science Cafe. I'm just giving everyone a minute to arrive, but welcome to those of you who are joining us on Zoom and to those of you who are joining us on Facebook. So hi, everyone. I'm Molly, and I'm with the University of Nebraska State Museum at Morrill Hall, and welcome to tonight's Science Cafe. So for those of you who are attending a Science Cafe for the first time, this is a casual evening of science with a social element. So feel free to grab a drink and get comfortable. And tonight we're broadcasting through Zoom and Facebook Live. So we'll be taking questions during the presentation. And so if you think of anything and you don't want to forget, you're welcome to put it in the chat box on Zoom or on the thread on Facebook. And we have moderators from Morrill Hall who are monitoring the chat, so we'll be able to get your questions to our presenters this evening. So for anyone just tuning in, I'm Molly with Morrill Hall. Welcome to Science Cafe. And I'm very pleased to introduce Bonita Sharif, who is an associate professor of computer science at UNL, and Cole Peterson, who is a graduate research assistant. So Bonita and Cole, thank you so much for joining us tonight.
Happy to be here, Molly.
Likewise.
All right, and without further ado, I will turn it over to you both. So thanks for joining us tonight.
All right. Thank you. Thank you for that introduction, Molly. So as you can see, we are going to talk about gaze, how we look at the world, but we are going to focus it on two main things: how we read natural text, basically English in this case, and how we read source code, how programmers program, what programmers program in. So let me tell you a little bit about myself, and then hand it over to Cole for their introduction. So I am an associate professor in the Department of Computer Science and Engineering. I have my lab here, which is located in the Shore Center, the lab of software engineering research and empirical studies. We do a lot of human factor analysis, and it's housed right literally under the stadium, south side. So what do we do? I'll talk a little bit about what we do in the lab. So I like interdisciplinary areas because they give you a chance to learn a lot about different fields and incorporate that into your own research. So I've been trained in software engineering. Okay, that is what I got my PhD in. But I want to talk to you about how we incorporate psychology ideas into software engineering. And the last time I checked, software engineers were also people, right? So it's very important to understand how people work with software, how they read, and so on. So we like to study how both students as well as professional developers work on software tasks. We all use software. We use a phone, right? Every day we deal with interacting with software. It's everywhere. So we want to understand how we can improve the process for developers to help them write better software. Our current collaborative project involves building this large infrastructure to make eye tracking accessible to other researchers. Cole?
So yeah, as Bonita mentioned, a lot of what we do is working like in understanding how students and professional developers read and write code. And that's what a lot of what I study particularly. Recently, I got done with a study looking at how developers work with multiple different programming languages and looking at the insights that can provide. And using that, we can provide better recommendations for when to use it and when not to use it, and other stuff like that. And with the current collaborative project as well, I'm one of the lead developers of it, and I'm the lead developer in Cereso Labs here at UNL for iTrace. And I spent a lot of time making sure that everything's working properly and building up this infrastructure to run eye tracking studies in the future, so it's easier for other people to do it.
Yes, and as you can see, Cole and I are in the exact same conference room, right? How did that happen? All right, so let me start off with the basics. I want everyone to understand what an eye tracker actually is. So I actually have one right here under my screen. This is basically what it is. It's a hardware device. Oops, thanks to Zoom backgrounds. It's basically like a bar, a hardware device that, and you can see some various other eye tracking equipment on the screen here. It has software embedded in it as well, but it's basically a collection of light sources and cameras. That the light source shines on your eye, it detects where the glint is on your cornea, and then based on where the glint is and your pupil is, it determines where you're looking at on the screen. So it's straightforward geometry. It's a mathematical model that they come up with to determine what you're actually looking at on the screen. There are many vendors, both small and large, that produce or manufacture these eye tracking equipment. We have a bunch of this in our lab in Shore. It's really cool to actually see how they work. So let me show you how the setup is in our lab. So it's nothing magical, right? It has a IR light source, an infrared light source that shines on your eye. You can't feel any fatigue, at least, well, only if you have epilepsy. Then there's a warning that you might not want to use the device because of the way it transmits the light. But this is the general setup we have in our lab. It's a 2-screen setup. On the left, there's somebody that's an experimenter that's conducting an experiment. And on the right, we have a participant that sits in front of that monitor. And you can see we have a webcam on the top of the monitor, but that's not the tracker. The tracker you see is at the very bottom. And here in the picture, you can actually see the light source in purple. Okay, it's usually not very visible when you're not taking a picture, but you can actually see it blinking and shining the light. Basically, that's what collects your eye gaze on what you're looking at on the screen. Okay, so that's pretty much what the tracker does. Okay, it gives you the coordinate on the screen that you're looking at. Okay, and then what you do with it is up to you. It doesn't know what that coordinate maps to or anything like that. It just says here, if you look at the origin to be, if you think of your monitor to be like a plane, right? And the origin is at the bottom left, then it gives you a number like 100, 100. That's basically 100 points to the right or pixels to the right, and then 100 pixels up. And it says you looked at this point. Okay, and that's it. Now, we use this information towards some functional goal, and I'll talk about that as part of our research questions. But first, I want to motivate as to why we even want to use an eye tracker, right? Because I don't want to use something if it's not going to give us something meaningful. Okay, it's not, you don't just use a cool thing because you have it. There has to be a reason why we're using it. So this is where the psychology aspect comes in. The whole foundation of using eye tracking to understand how people work is based on 2 things. It's based on the eye-mind hypothesis and immediacy theory. And what does this mean? Okay, what is the eye-mind hypothesis? It basically says that what you're looking at, what you're fixating on for a certain point in time is what you are processing in your brain, okay, at that time. And then the immediacy hypothesis says you immediately, so the information is immediate, so it doesn't take long, you don't have to wait long. This is why it's very important to understand what you're looking at is what you're processing, and then you make some decisions based on it. Okay, so it's directly perceived right after it's looked at. Okay, and this is fundamental because it is really the basis of all of our results that we're actually trying to derive. Okay, especially decision-making processes and why did people do something the way they did? What makes a novice different from an expert, right? All of these things are kind of important questions to ask because then we can help maybe a novice become an expert at a late, much quicker. Eventually they will if they stick with it, but we want to reduce that gap from novice to expert. So yes, why use eye trackers? They allow us, because of these 2 fundamental hypotheses that were published, I can go back in 1980, so not too long ago. It allows us to analyze eye movements for different tasks. It lets us know what a participant is doing while they're doing it. So while they're think of yourself back in school when you actually had to solve, let's say, math problems, right? And I always had a math teacher that was really brutal. They would always give me a 0. Okay, even if they only looked at the last answer, not my process. So if I got 3/4 of the way correct and the last 1/4 was wrong, my final answer was wrong, but I didn't get any credit for the thing that was correct. Here, if you actually look at the person solving things, as they're solving stuff, or even learning how to, it doesn't have to be math. It could be physics. It could be any subject. You can now see what they're doing while they're doing it versus just looking at the final answer, right? So it gives you this sort of, I call this the glass box or the white box analysis, because it lets you see the thought process, but more importantly, without asking you. So I'm not asking you every second, what are you looking at? What are you looking at, right? I'm getting this data as you're actually looking at it, which is crucial, because as soon as you interrupt someone and ask them, what are you looking at? You've already messed up their thought process, right? So this is like an implicit thing that's collected while you're working without interrupting you. So it's a really nice method. Alternative to, of course, think aloud, where you're asking a person to verbalize their thoughts, and questionnaires, right, that you have online. We have all taken surveys. So I see it not as a replacement. I don't see eye tracking as a replacement for surveys. I see it as an addition that can give us added insight into how people actually work. Okay, so real quick, I mentioned this a little bit before, but how do they work? It's not magic. It basically has a bunch of IR lights and cameras. Depending on the eye tracker, you can have one or more. And it basically shines this light on your eye based on where the glint is, like I said before, and how the light hits your retina and comes back out through your pupil. That vector basically tells you what you're looking at on the screen. Straightforward geometry, nothing magical there. Okay, so I like this cool graphic because this was done not by me, but this was created by one of the magazines we wrote an article for. All right, so just quickly some terminology before I get into the source code and the natural text study we did. So there are 3 things I want you to know: fixation, saccade, and scan path. Fixation is, we all do this. We all fixate on certain things when we are looking at something. And then when we move from looking at one thing to another thing, we perform a saccade. That's a quick, jerky movement between fixations. Okay, our brains are designed in a way, or we're designed in a way such that our brains can process information such that they will not explode. For instance, if there was information processing occurring every single time you made a saccade, our brain would not be able to handle it. So there is actually no processing that occurs, and you cannot notice this because it's really quick, but there's no processing that occurs when you move from one fixation to another. So during the saccade, you absolutely do no processing, okay? But when you're fixated on something, you basically stabilizing your eye on a certain area on the stimulus, and the stimulus here is just the screen. You're actually processing information and learning what to do with it. And then a scan path is basically just an ordered sequence as you go through the different fixations. So on the right, I show you a picture of, this is C++. This is a source code that usually software developers write code, right? This is one example of it. And it doesn't matter what it does, but we just tracked one person here, and we're showing here a gaze plot. And what a gaze plot is basically it maps fixations on different points of the code on the screen. You can see some circles are bigger than the others, which means you spent more time looking at that, okay, versus others are smaller. A scan path would be, if you looked at, you can see it right on top here. This is fixation 1, so they started reading it here. And then 2 is somewhere here, probably there's 3. So a scan path would be 1, 2, 3, and wherever 4 is, okay? It could be a subset of this gaze plot. Now, these are very important terminology because we actually use these as metrics when we're getting data. And I do cite the papers that reference these for interested individuals if they want to look at that. So visually, you can think of, so this is a line of code in C++. Visually, you can think of a fixation as that circle there, and the saccade as that arrow going from, let's say, looking at the word public and then looking at void, okay? And usually they are between 200 milliseconds, 200 to 400 milliseconds, and then the saccades are much smaller because they move, right? Another thing I wanted to point out is when we're looking at this statement and we're reading it, and we are looking at the word public, generally you have high visual acuity, your visual, focus is higher on the word public. You might see static in your side view or your the periphery, but you're not able to see it very crisply, right? It could be blurry on the side. So this is, our brains do this so that, again, they don't explode, because you have this, every one of us has this certain angle which we can see very clearly, and the rest is, even though we can see it in our periphery, we can't tell details about it. For example, in the Zoom, if I'm looking at Molly, for me, Cole is right under. I can see Cole, but I cannot tell anything else, like what's the expression, let's say, on the face. So this is important to understand too, because that brings me to the drawback of eye tracking, which I'll refer to later. So, but just keep that in mind. So this study is actually published in a paper. I'm definitely not going to read this to you, but I thought I'd have it here because it really is one of the first times people really systematically, my collaborators and I systematically went through the process of really understanding what is it and why is it that code is different from natural text. Okay, why is this happening? And we wanted to understand why. So let me start with how we read text, right? So this is the fun part. Now we get into, now that we have like the background and some terminology down, let me talk about the experiment. So linear reading is typically done left to right, top to down. We're just considering English, right, in this case. So we call this the story order. This is a piece of code snippet here. We don't typically, an expert who knows how to read code will not read this top down. They will basically go to the main method here, read it here, then jump up and do several jumps around to read this. We call this non-linear reading. And so the two main things we wanted to figure out in this study is, do the linear trends we observe when we read English, natural text, do they hold for people who are novices at source code? In other words, if you have no background in actually programming, do you read code the same way as you read English? And then we wanted to operationalize this linearity via some metrics that we could collect and measures that we could test. Okay? And we really wanted to see how experts differ from novices. Okay, so that was our second question. Now you would think this is very simple and someone might have done this before, but guess what? We looked in the literature. We couldn't find anything that actually truly operationalized the linearity metric. Okay, so we decided, okay, we're going to do a study. Okay, so we collected data from 14 non-CS students. These were the true novices. They did not have any programming background. Okay, and then we had 6 professional programmers. These were the experts. Okay, and we sat down and we thought about how we can actually operationalize objectively linearity in terms of, how do people read code and how do they read text and how can we compare? So when we brainstormed, we actually came up with these measures, and they are based on fixations and saccades I talked about before. Okay, so we have, you can see here 1, 2, 3, 4, 5 linearity measures, and then we have a bunch of things here. So let me explain. They might have fancy names, but actually they're very simple. So let me explain quickly what vertical next text is. It's the percentage of saccades that are on the same line, that go forward on the same line, or move one line down. Okay, so if you're on this first line, it's the percentage of times you go forward or one line down. That's vertical next text. Vertical later text is the same thing, percentage of forward saccades on the same line or any number of lines down. So you could be skipping here, reading this and then skipping all the way down here. Okay, that measures somehow linearity or the converse non-linearity, right? Then we have horizontal later text, which is the percentage of forward saccades within a line. Regression rate, this is an important one because regression, what is a regression? A regression happens when you reread something over and over. Okay, reading research shows that when you have a regression, you tend to have trouble understanding it. So this is why you go back and reread it over and over. So regression rate, we measured this as the percentage of backwards saccades. So if you were here on this line here and you went backwards any amount, we call that the regression rate. And then we have a line regression rate. It's the same thing, but only if you go back on the same line. Okay, so we thought these kind of justified the concept of operationalizing linearity in these 5 measures. Then we also looked at saccade length and element coverage. What is saccade length? It's basically just the Euclidean distance between 2 points. Basically just the distance between 2 points. The basic distance formula that we have learned in elementary school, right? That's what it is. And then element coverage is just the percentage of things people looked at on the screen. So I'll give you some examples of this. So let's go right into the results. Okay, so we found when we did this that code reading was more nonlinear. Okay, in particular, when we looked at the regression rate, we found that novices have 31% of regressions and experts have more. You would think the novices have more, right? But what we have found that when you have certain things in the code, the experts tend to take, first of all, they tend to take the study more seriously because they're just more invested in things. This is for generally all studies. And second, it could be that also for particular things where you have like loops in the code, you might want to have regressions. So they keep going back and tracing the loop. For natural text overall, we found the regression rate was much less than code, which also tells us that code is much more nonlinear. We graphed this thing, these measures, we graphed them and compared, we ran all the stats tests. I think they all check out because this was a peer-reviewed paper and we have the data set online. We basically found a significant difference. These 3 asterisks basically just says that there was a significant difference between the 2 groups means for those measures. So you can see here, for example, for regression rate, novices had more regressions than experts. Here for vertical later text, meaning the number of saccades that were one line down, one or any more lines down was also significant, and so was the next. Okay, so let me show you an example of coverage now. So this is an example of code here. This is also C++. And, oh wait, yeah. Yeah, so here we had, you can count this, I'm pretty sure it's correct. You have 29 elements here. So public is one element, class is another element, and so on. When we looked at the number they actually looked at, it was not even close to that. It was just 9. And they're listed here in blue. And we have, 31% versus almost 70 was not looked at. And it makes sense because there are some things here that are really boilerplate that people don't necessarily look at. I mean, they might see it in the periphery, like I said before, but we have no way to really tell if they read it or not, because that's, again, one of the drawbacks of eye tracking is we can't really say if somebody looked at something or processed information when they somehow got this information from their peripheral vision. Okay, that's definitely a disadvantage. We also looked at how people look at the number of elements, and when we took at percentages, we found novices had about 52% that they looked at, whereas experts looked at less. Now, this tells us something. It basically says experts know how to hone in on the most important parts of the code. So they don't necessarily look at everything. So it makes sense to have less looked at than novices. And then here for natural text, 83% was looked at. So approximately we skip 15% of the text. And here almost 60% was looked at. So less was skipped. So then what we did was we wanted to compare the story order and execution order. Without going into too many details, we basically mapped the I signal that we got from the line across time. So if you think of this as a line of code from 1 to 5, this is an example, and you think of the x-axis as time, this red dot tells you that you looked at that line. Okay, so here this person started looking at line 4, then they went to line 1 and they read it for some time, then they went to line 2, read it for some time. Notice how this is a pattern that's occurring twice in this sequence of gazes. And we call this the scan pattern. So it's really story order. You're reading it, right? You're not really skipping up and down. We have this mathematical model that we generated and tried to map it to this different, I'm not going to get into details, but of the actual model, but basically what we tried to do is find similarity between what they're looking at per line and what the gaze is actually giving you. Okay, and then if it's similar to going from one line to the next, then it's higher similarity with their gaze. If it's not going from one line to the next, and instead it's very nonlinear, then it's considered execution order. But we had a very systematic way of actually doing this. And we didn't just look at the data and eyeball it, right? We actually wrote an algorithm to compare it. And that's what you see here, the naive score and the dynamic score. Okay, so here we can see an example of fixations that go reading in story order, whereas here on the right, we start from main, we go to print method, and then immediately the person jumps here and reads this for loop, okay? And this is considered close to story execution order. This is one example of a novice actually reading some source code. Sorry, I previously said that was C++, that was Java. This is C++. This is a novice programmer actually trying to understand what this code does. And you can tell this, we did some other analysis too, but you could tell this because of the large fixations they have in this code, which is a nested for loop, which is actually harder for novices to understand what it does. Okay, so in summary, what we found is after coming up with those measures to operationalize linearity and compare code with text, we found that source code is a lot less linear in reading, even for novices than experts. Experts definitely had this nonlinear aspect even more. We also found that reading code, people don't necessarily focus on as many elements as they do in natural text. And then we found that also for experts themselves, when we looked at them, we saw that their behavior is definitely explained by execution order, because once you become an expert, you know exactly what to look at. And you can skip the other sort of the boilerplate that you're used to. So what does this all mean, right? It's important to understand, okay, we did this study, we found these cool results, but what does it mean? So there are three things I think that we need to understand here, or at least target in terms of stakeholders. Okay, so for the practitioner, this is the person who works in industry, right? They are a full-time developer. Maybe we can come up with good coding practices, right, for readability. Understand how to write code in a way that it makes it easy, not just for that person to understand, but also for others. As an educator, we can teach our students how to better read and write code. Okay, I certainly was not taught how to read code when I was in my undergrad. Okay, we don't teach them how to read. We just tell them, hey, go and write it. But do we start learning English by writing it? No, we learn how to speak first. We learn how to read first, right? So the same applies here. And then hopefully, we are hopeful that eventually we'll come up with these new theories that explain the differences between novices and experts. So this is just the first step. we're definitely very excited about the results and want to do in the future this longitudinal study where we follow a person across time and see what is the point when a novice actually starts becoming an expert, right? Is it a certain point in time? Is it is it a few months? I mean, what is that thing that says, okay, now I actually understand this, or much different than I did before, right? And then we can do so many other testing. Cole's working on some of these for the PhD program, but we can look at various other things. Basically test language features and see how they play a role in comprehension. And we want to build, eventually, our goal is to have program designers or programming language designers listen to the data, right? You don't want to build something that is going to be hard for people to use. We want to make sure you're creating a feature in a language that is actually useful for people to actually use and programming. All right, so I want to end with this slide, and then I have a bunch of videos to show you. This is a picture taken in about, I think, the 1960s. Okay, the picture on the top left is an image that was shown to the same person, but based on the task, our eye movements are very different. So they were shown that picture, and in the first one, they were just told, examine it freely. And notice how their eye movements were, just all over the place. You couldn't tell what exactly they were focusing on. They didn't have a focused task. The second one, it says, estimate material circumstances of the family. Notice how this maps to the top here. So they're looking at what's on the walls. They're looking at, perhaps the wallpaper, the chair. They looked at a little bit. You can see these that map there. The third one, and note that this is the exact same person looking at that picture, just with a different prompt, right? In the third one, it says, give the ages of people. Look at that. What are they looking at here? The face of people, right? So we are driven by a prompt. You cannot just tell a person, okay, look at this image. You have to tell them what to look for, and our eye movements will change based on that. And so on here. So this is, remember, the clothes worn by people, and you can see them literally looking at the clothes, right? And so on. This says, remember positions of people in the room, and you can see they're looking all over the place to make sure they remember. So I always tell my students, what is the one most important thing in any experiment design that can make or break your study? It's the task. Okay, because if you don't prompt the right way, you are not going to get what you're looking for. Okay, so these are just our contributions again. I'm going to skip this and I'm going to go right into this. Cole?
Yeah. So as we presented a lot of things, it can get a little bit complex with all this new stuff that we're talking about. So I just wanted to bring it back to the fixation patterns and looking at the differences between natural language and source code. So we can see here that I'm reading this code or reading this language right here, and we can see that the fixations go from left to right, line by line. And you can see right there, one fixation was longer, looking at it a bit longer. And there's different patterns and different cognitive load that we can extrapolate and pull from this data to see how hard it was for me to read this or how hard it would be for somebody else. But if we move over to code, we know that there are multiple different ways for us to read it. Here we can see if this plays, I read this code in story order. So I read this from top to bottom and just read each single line. And while experts definitely read code like that sometimes for small sections, that's not the overall trend that we see. And while I'm not pompous that much, but I do consider myself somewhat of an expert. So my fixations probably are a bit more into the next stimulus here, if we can show. And this is the execution order, looking through and seeing, if it goes, and reading the code, the constructor gets there and seeing how the code would execute as it goes through. And this is a lot closer, even though it does seem complex. If you know code, if you understand it, it makes more sense with this domain knowledge that gets added on. But it looks very different from the prose reading specifically, and it looks even different from the story order reading from top down, right to left. And ultimately, that's what it comes down to. There's a lot of differences that we can pull from eye tracking, not only if they all look very similar, we can pull information from fixation duration, regression rate, all this other stuff. But the entire how it looks is so different than natural language text, and we can learn so much information from this.
So can you imagine showing this to a person who's just started a computer science, a software engineering program, right? And say, and the instructor basically shows this instead of saying, go and write your first program. I can already see the benefits that could have for just teaching computer science, let alone forget about the practitioners, right? It would be awesome to see this live instead of like just telling somebody that this is where you look at it. It's different when you see it. And with that, we actually conclude our presentation, and we are happy to answer any questions people have.
Well, thank you. Yeah, thanks so much. That was really interesting, and I appreciated seeing the videos. I'm sure everyone else enjoyed that as well. So yeah, this is just a good chance to remind everyone that you're welcome to put any of your questions in the chat box or in the thread on Facebook if you've thought of anything you'd like to ask our presenters tonight. I did see that we had a couple questions come through. The first was, in your study, how little experience with code would someone have to be considered a novice?
So for this particular one, we made sure that they were true novices. With nowadays with STEM education, everyone knows a little bit of programming, even in elementary school. This entire study was actually conducted in Germany with my collaborators there. And they were people who had no experience whatsoever, not even with block, languages or anything like that. So they had 0 years of experience in coding.
Great, thank you. And kind of in a similar vein, we got another question of how did you recruit both novices and experts, since those would be probably 2 different recruiting pools of folks?
Yes, recruitment is it's a very different process, but yes, it requires a lot of effort to make sure you publicize it right, and of course, the study does have approval from all the places that it needed to have. But the thing is, when you recruit from industry, you always make use of your personal contacts. Okay, that's one. Okay, so you can publicize it on social media, you can publicize it within your circle. For students, it was easier because all we had to do was go in and, I didn't do this, but what they did was they went into classes and announced it. Okay, we do the same here at UNL. We go in and announce the study in classes, and then people volunteer. But it's 2 different things. I would say for industry, you definitely have to depend on your personal contacts.
Thank you. And then another question here. So what inspired you and your collaborators to test novice versus experts in reading source code in particular?
Yeah, so I've been trying to, for a long time, be able to automatically detect what makes an expert an expert. Okay, this is actually not a trivial task, because when I look at 2 experts, they might have the same result. They solve the problem in the right way, but their method of getting to that answer is very different. So I wanted to get as much data as I could collect, and we're still in the process of this actually, because the more data we can get, we can see similarities, right? Because I am sure there are similarities between experts and between novices, but there are still a lot of individual differences. So my goal eventually is to figure out what those individual differences are and somehow come up with a model that extracts those out and comes up with also the commonalities. And I think that's what we're trying to do. And that's a very interesting problem to me, there is no easy solution, like I said, because of the way we work as humans, but there has to be something common because, the experts get it right. They just do it differently. So if I took two experts, there's a very low chance that both of them looked at the same thing at the same time. So that's intriguing to me, is how can we figure out a way that gets rid of all those differences, but also looks at the commonality. And that's what led me to actually look at this project. The more data we have, the better it'll get. Right now, our main problem is we don't have as much data as we need, because I have to note here, running the study is very labor intensive, right? Somebody has to sit down there and actually track the person that comes to our lab. We do it one at a time. It's not like a survey we put online and 200 people can take it, right? This is literally somebody that needs to come to our lab, or we need to go to them at their location, which we have done both, and actually collect the data, right? So it is a labor intensive process. And this is why it takes a few years to get a data set large enough, then we can see these differences. But I'm confident that at some point we will be able to see that.
Yeah, and with the participant recruitment and stuff, the man hours that go into it, my thesis that I did, it had around 31 participants, and it took probably an hour to maybe 2.5 hours for each single participant to run them. And that doesn't take into account the recruiting, the involvement, and setting up, testing, and everything else that goes into a study itself. So it's probably 80 hours of just running the study to get just 30 people. It's a very intensive process.
But so rewarding, Cole.
Oh, it is. Yes, very much so.
We absolutely love what we do. Wouldn't you? You have fun gadgets to play with every day in the lab. You have state-of-the-art trackers. Why wouldn't you
Oh,
like
yes.
it?
No, it's very good. State-of-the-art tools and everything else like that. Very much enjoy it.
Great. Well, thanks. Yeah, I think I think that's a really good point to think about, all the recruiting. I guess I can say for part of my job, I recruit volunteers for the museum, and similarly, it always takes a lot longer than you think, with all the back and forth and coordinating and schedules and things like that. Great. Well, and so you talked a little bit before about some of the differences between different types of code. Like different, I'm gonna get it wrong here because I'm a super novice, but maybe you said C, TT, and Java and things like that. And so have you done studies that are looking at how people's eyes move across compared to different types of code?
Actually, that's a very good question. And it was, you sounded like an expert, Molly, asking that, because that's exactly, you hit the nail on the head. That's exactly what Cole's working on a paper related to that. So, let me name some languages. You've probably heard these before. Python, have people heard this name? It's another language. C++ is another language. Java. So there are so many, every day there's a new language coming out. Okay, so, but if you know the foundation, right, you can adapt to different languages, right? But still, it's different. The syntax is different. Sometimes, some languages require certain spacing, like Python, for instance. So I did a study when I was back at Youngstown State on differences between eye gaze behavior between two of those languages, Python and C++. And Cole's working on the write-up of that actually now. We're just, it's finals and all now, but we're planning to submit it right after. But we wanted to see, does the language paradigm have any effect on how people read? And so, yeah, that's still in process, but we are looking at that. Yes, it's hard because we need to, so reading studies are easy to do in psychology because they can pull from the sample population, which is everybody. Do you know who we need to pull from? Programmers, and we don't get enough of them, right? And so our sample to begin with is already, the total pool is smaller. Okay, and then it's also when we want to compare, other things like age, gender, and so on, it's also hard to find a balanced set of, males versus females, for instance, and compare how they read code. So Yeah. But we are doing that.
Yeah, thank you. I mean, we have a question here from Jody. Have you done anything with block-based programming versus text-based programming?
Not currently. I know at least one team that has done that. But that is something to look at as well, especially with kids. I would be interested in seeing, for example, how people use Scratch Junior versus C++ or Java, especially since the AP CS principles course is taught in Java completely. Compare that with, let's say, Scratch that they learn in Scratch or Scratch Junior, they learn in elementary. But I have not, but I know at least one team that has done, but it's, again, very simple study. I feel, there are so many studies you can do. You have to prioritize and think, why do you want to do this? So my question to Jody would be, why are you interested in studying this? And you have to make that case, right? Because I don't want to just collect data for the sake of collecting data. What will we get from it?
Yeah, that makes a lot of sense. Our next question here is from Garrett. It says, how did you decide to study this aspect of science, and what was both of your path to this career?
Cole, you want to go first?
Oh, my path to this career was I went to UNL, and I saw Bonita talk about her research, and I was like, that sounds cool. So I did it. That's really it. There's less. Basically, I just stumbled into it, and I'm very happy I did. But really, what appealed to me about it is like, I enjoy writing code. I enjoy reading code. So understanding the underlying processes behind how does that work, understanding what makes an expert, and how do these processes and behaviors build and develop over time, and giving empirical evidence to help people out in the future. That's what appealed to me when I first joined. And I mean, I enjoy contributing to that now as well, but my path is basically just Bonita.
I have a better story. I mean, I can tell you about mine. But Cole's been amazing, by the way, in the lab. Just all my students are amazing. So I started as an undergrad. I just wanted to do computer science, okay, as an undergrad. I remember, this was way back. I still remember it though. I loved animated movies, and I actually wanted to make them. Okay. Little did I know I was not going to be successful with it. I mean, obviously, tell that to a 17-year-old. Okay. I have a 14-year-old. Trust me, I know how it goes. So, but I thought I wanted to be, I thought Pixar would hire me and, all of that. Right. So I studied computer science. Cole, did I tell you the story?
I'm not sure. I don't believe so.
I wanted to study computer science because I wanted to create these movies, animated movies. Till today, I love animated movies. And so then when I got in, I actually liked what I was doing. And then I forgot about that. Thank God I forgot about that. And I liked, what I was doing, the projects, the algorithms, the programming. It really kind of clicked. It didn't click early on, but stick with it. Okay, if you stick with it long enough, it will eventually click, and you have to put in the hard work, obviously. Cole, we do work hard in the lab, right? But we also know how to have fun.
Oh, definitely on both counts. Yes. Work hard, play hard.
Absolutely. So that's what got me into the field. And then I went on to do I've completed my bachelor's degree in computer science in Cyprus, actually. And then I moved here to Kent State University. I did my master's. Even then, I didn't want to do my PhD. I was like, okay, I'm just doing my master's and I'm going to go get a job, right? But then my now advisor, or then advisor, I did a advanced software engineering course with him. And he was like, you need to come into my research lab, just attend my meeting. I was like, why is he asking me to attend this meeting? I was like, did I do something wrong in the course? But actually he wanted to recruit me into his research lab, because he's like, you're doing so well in my course. Why don't you do research? I'm like, then does it mean I have to do a PhD? He's like, yeah, it'll be fun. You should do it. And he was right. Till today, I keep in touch with my advisor. He's amazing. He taught me how to do research. I owe everything to him. I hope I am that for my students as well. So, and here I am. I spent, so I graduated in 2010 from Kent State with my PhD in software engineering. And then I moved to Youngstown State, where I worked there for a while. Actually, I worked at Ohio University for a year. Then I moved to Youngstown State, and then I moved to UNL when they had this position, which really matched my description. They were looking for someone in software engineering and human computer interaction. And they had a lab. I mean, who has space nowadays, right? They had a lab for me. I was like, okay, that's it. This is the best offer I can. So I took it, and I'm here. And after that, the rest, yeah, Cole told you.
Well, great. Thanks so much for sharing that. Those were some fun stories, and I guess some similarities between the two of you, that you had a mentor who inspired you. So, well, great. Well, thanks so much. I'm not seeing any more questions coming in. So I just want to thank Bonita and Cole again, and thank you for this great presentation. Thanks to all of you for your great questions, and thanks to our presenters for answering all of them. We really appreciate you all joining us tonight.
Thanks for having us both.
Mm-hmm.
Yeah,
Thank you
Thanks
so
everyone
much.
for listening.
Yeah, and our next Science Cafe, if you enjoy this talk, is going to be on May 25th. It's called Stressed, You're Not Alone, Especially at the End of Life. And it's with Katie East, who is a PhD student in anthropology. So we hope to see you there. You can learn more about that, as well as visiting the museum and our other programs on our website at museum.unl.edu. So yeah, thank you again to our great presenters tonight, and thanks to all of you for tuning in. We hope to see you at another program soon.
Bye.